students. In this lecture, I'm going to explain another essential uni physics D5.6. This is A-level physics here. So I will explain. First, this is part A of the D5.6 about the lowest frequency. Wind instrument is 60 centimeter long and can be modeled as a tube with one closed end. So here we have a closed end. This is problem with the organ pipe or wind instrument that has the close at one end. So and open another end. So what is the lowest frequency that can be placed in on this instrument? So we have to find the lowest frequency. So in order to find the lowest frequency, first of all we need to have the diagram first of all. So the diagram is basically the organ pipe that has closed one end closed and the fundamental frequency is here. Okay, so here is the organ pipe. One end is closed. This end is closed at one end, and other end is open here. So as we know that when the organ pipe or the wind instrument is closed at one end, the open end both has the antinodes. At the open end we have antinodes, and this is first fundamental frequency, first harmonic, just like that. So at the close end we have the node. So at the close end we have the node, and we have to find the lowest frequency. So simple formula for frequency is F is equal to V over lambda. As we know that we use wave equation, V is equal to F lambda and F is equal to V over lambda. So first we need to evaluate the value of the lambda wavelength. So what is the wavelength? So in order to find the wavelength, this is the length of the organ pipe, that is equal to capital L. This length is equal to, as we know that this length is equal to the consecutive distance between node and antinode. As we know that the consecutive distance between node and antinode is lambda by 4. So we can see that L is equal to lambda over 4. Okay, how it is lambda over 4? I will explain here. For example, if we have any type of node, if we have any stationary wave, so if for the stationary wave, the one complete cycle or one complete of wave is this one. This is the one complete wave. This green color is the one complete wavelength, and this length is actually one lambda for complete wave. For complete wave, we have the length of lambda. So this is for the node to node distance. Consecutive distance between node to node is half of that, and consecutive distance node and antinode. If this is antinode and this point is node, so the consecutive distance between node and antinode is lambda over 4. So this is half and half. This length is lambda. This node to node distance is lambda by 2, and node to antinode is lambda over 4. So a simple formula is that if we have the same thing, node to node distance is lambda over 2, antinode to antinode is also lambda over 2. But if we have a node and we have antinode, so we have the distance lambda over 4. So the L is equal to lambda over, because one is antinode, other one is the node. So the consecutive distance is lambda over 4. So here we can find the wavelength, that is equal to 4 into L. So the length is 60 centimeter. So 60 multiplied by 4, we have 240 centimeter. So wavelength is 240 centimeter. Okay, now we can convert this wavelength into meter. So this is 2.4 meter. So wavelength is lambda is equal to 2.4 meter. Now we put this value in the V is equal to F lambda. This formula, V is equal to F lambda, F is equal to V over lambda. F is equal to V over lambda. So we have velocity is 330 meter per second, speed of sound is 330 meter per second, and wavelength is 2.4 meter. So our final answer is frequency is equal to 137.5, and we round up this value to two significant phase. Which gives us 140 hertz. 140 hertz. So 140 is the required answer. Our correct answer is 140 hertz. So this is our correct answer. Now for the second part, this is first part. Okay. Now for the second part, if the note of second lowest frequency were played in the instrument, state the position of note. So we have to explain the second lowest frequency, the position of the node. So in order to find this, first of all I make the diagram for this. So the diagram for the second antinode, second harmonics or second lowest frequency. So we have this, and then this is the second harmonic, second lowest frequency. That's the second harmonic. So at the, as we know that at the close end we have node always, and this is antinode and this is node, and at the open end we have always antinodes. So we have to first find the consecutive distance between node and antinode. So total distance from this node, towards this antinode, we have to eliminate, find the this distance total. So as we know that we have in between, we have node to node. This is node, this is node. Node to node distance, then antinode. So total distance is divided into two parts: node to node and plus node to antinode. So we have total length is equal to distance between node to node plus node to antinode. So node to node, as we know that node to node and antinode to antinode is lambda over 2 plus node to antinode is lambda over 4. So we have to find the 2 to 4, and we get the wavelength that is equal to 3 lambda over 4. If we solve this to 2 lambda plus 1 lambda, this will give us 3 lambda over 4. So ultimately we can find the wavelength lambda is equal to 4 over 3 into L. 4 over 3. The length of the air column is 60 centimeters. So 60 centimeters. So we get 80 centimeters. We divide this, we get 80 centimeters. So wavelength is 80 centimeters. We know the wavelength is 80 centimeters. So if wavelength is 80 centimeters, so consecutive distance between node to node is half wavelength. This distance is half length. As you know that node to node relative distance is half wavelength. Okay. So at this end, at the when the when end is one end is closed, so one node is at the close end. So our required option is, there are three options. One at the close end, this is correct, and another 20 centimeter from the close end. So another is from the 20 centimeter from the close end, another from the 40 centimeter from the close end. So there are three nodes in this. He says this option A says that there are three nodes, one at the close end, other one, second one at the 20 centimeter away, and then 40 meter away. So this is wrong, because for the second lowest frequency, lowest possible frequency, or the second harmonic, we have only two nodes, not three nodes. So this is wrong option. So one 20 centimeter from the close end, another. So as you know that when we have a close end, so at the close end we have the node. So this is also wrong. This option is also wrong. The third one at the close end. So as we know that one this end we have the close end, node is at the close end, and another 40 centimeter from the close end. Okay, now we check this option, another 40 centimeter from the close end. So we have to find the consecutive distance between two nodes. As we know that consecutive distance between two nodes is actually lambda over 2. So our wavelength is 80 centimeters. So we divide by 2, we get 40 centimeters. So our consecutive distance between two nodes is 40 centimeters. So that's why we find the wavelength for this problem. So that's 40 centimeters. So first node is at the end, at close one end, the close end, and the other is away from the 40 centimeter from here. That is the 40 centimeter. Okay. For the third option, third possible or third lowest frequency, we again draw the same diagram. We have the three harmonics there, and there is antinode at this end on the left hand, and we have then node. Then this is one harmonic, second harmonic, and this is third harmonic. So this is third harmonic. So this end is node, then this is node, this is also node, and this is antinode. So we have total. We have to find the total length again. So at the close end we have node. At one end we have a node. So this option is the correct one. But another 24 centimeters. So we have to check and this consecutive distance between two nodes, second node and third node. Okay. So in order to find the consecutive node distance, we first find the wavelength. So L is equal to, as we know that this total length is divided into, from this end node, then node, then node, then antinode. So we have three nodes and one antinodes. So we have three node to node distance, plus one antinode, one node to antinode distance. So three node to node distance. So node to node distance, we know that is lambda over 2. 3 into lambda over 2 plus 1 node to antinode, that is equal to lambda over 4. So we solve this 4 2 3 to the 6 lambda plus 1 lambda, that is equal to 7 lambda over 4. So L is equal to 7 lambda over 4. So lambda is equal to, clearly here, lambda is equal to 4 over 7 L. So lambda is equal to 4 over 7. So length is again 60 centimeters. So we have 60 centimeters. So wavelength is equal to 40. It's when we solve, we get 48 centimeters. So if wavelength is 48 centimeters, so conductive distance between node to node is, as we know that conductive distance between node to node is lambda over 2. That is equal to 48 centimeter divided by 2. That is equal to 24 centimeters. So we have this node to node distance is 24 centimeters. So first node is at the end. So this option is correct. Another is 24 centimeter from this end. So another is also 24 centimeter. From this end we have 24 plus 24. This will be at 48 centimeter from this node. So this option is correct one. This option is correct. But so B option is wrong because one is at close and this is correct option, correct thing. But another 20 centimeter from the close end, another 40 centimeter. So this is wrong because not 20 centimeter is 24 centimeter. So at the 30 centimeter, so this is also wrong. So the A option is the correct one. One at the close end. This node is at the close end. The other is, the second node is at 24 centimeter. Third node is again at the